Hi Amit. Hi Ankit, sorry. Hello everyone. Can you hear me? Hello? Hello? Can you hear me? Hello everyone. This is Manjeet and I am TA for this course, the nature and the properties of the material. So today we will do the assignment number 2, and this course is run by the Professor Ashish Garg, and today we will discuss the this assignment 2 that is based on your week 2 tutorials that is on the NPTEL course. So we will solve all the problems one by one, and then after we will discuss also. If you have any kind of the problem, please let me know, or either message on the chat box. I can see from there also and will respond accordingly. Okay, and uh, please feel free if you face any kind of the problem, and can stop me and ask me any kind of question also. Okay. uh yeah, Tino, can you mute yourself? I mean, because your is unmute. I can't hear you. I mean, ha, yes, now I can hear you. Please mute yourself so that nobody, you don't have any disturbance, but still just mute yourself. Okay. So today this is the first question where it is asked that it has a unit cell that having a is equals to 5 angstrom, B is equals to 8 angstrom, and C is equals to 3 angstrom. Alpha is 90, beta is 65 degree, and gamma is the 54 degree. The space lattice for the unit cell is orthorhombic, uh, monoclinic, rhombohedral, and the triclinic one. So first we will discuss all about these crystal structure, and then we will discuss this question. So in orthorhombic, we have in orthorhombic system we have A is not equals to B and B is not equal to C. Alpha is equals to beta, and beta is equals to gamma, and that is equal to 90 degree. In monoclinic, we have alpha that is not equals to B, beta B is not equals to C, but alpha equals to gamma that is equals to 90 degree, and beta is equals to not equals to the 120 degree, that is not equals to the 90 degree. Okay, in the rhombohedral one, where lattice parameter A equals to B, B equals to C, and alpha equals to beta that equals to gamma but are not equals to the 90 degree. And the third one is the triclinic one. In triclinic one, we have alpha equals to not equals to beta, and beta is also not equals to C, where alpha not equals to beta and beta is not equals to gamma, and that is also not equals to 90 degrees. So in Just a second. Okay. Okay, so in orthorhombic we have A is not equals to B, B is not equals to C, and alpha, beta, and gamma are equals to the 90 degree. So in this question we have A is equals to 3, B is equals to 8 angstrom, and C is equals to 3 angstrom. Alpha, beta, and gamma all are have the different value. So alpha is not equals to beta, and beta is not equals to gamma in this. And here also A, B, C are also not equals. A equals to not equals to B, and B is also not equals to C. So which of the following are which of the crystal system this belongs to? This cell, this unit cell belongs to which of the crystal system? We have discussed all the orthorhombic one and the monoclinic, rhombohedral, and the clinic. If I see this one, triclinic one, here also the same condition apply here. A is also not equals to B, and B is also not equals to C, and all the angles of the crystal structure are also not equals to 90 degree, and are also they are not equal. So for this unit cell where A, B, C are not equals, and also the angles, their corresponding angles are also not equal to the 90 degree, and also they are not equals to their values. So this unit cell belongs to triclinic one. Yes, this is the triclinic one. Okay, so this is our first question. So if you have any other, if you have any doubt in this question, please let me know. Do you have any doubt till this point? I haven't received any response, so I am just assuming you guys don't have any queries. So let's move to the next question. That is the question number 2. Okay. So in this question, it is asked, what is the shape of the primitive cell of the FCC lattice? You all know about the FCC? You all know, yeah, FCC, we have in FCC, if I'm talking about the FCC cubic one, FCC cubic is basically where the atom are all present also on the face of the cube also. Okay, this is my cube. If I am assuming this is my cube, and atoms are all present at the corner of the cube also, and at the center of each face, or each face of the cube, here, here, of center of here, and of this one here, and somewhere up, and the this one also here. But here it is asked the shape of the primitive cell of the FCC lattice. You know FCC having the two atoms, because 8 atoms are at the corner of the cube, and plus 6 that are at the face center. So if I calculate number of the lattice point, that will be the 8 into 1 by 8, because the contribution of the each atom at the corner of the cube will be the 1 by 8. So we have the 8 number. So 8 into 1 by 8, that give me the 1 atom plus 6. 6 atom, total 6 atom at the face center. And because each face is shared by the 2 unit cell, so this will be the, because the contribution to the 1 unit cell, because each this phase, if I'm talking about the this phase, so if I draw the another unit cell here, let's see, if I'm drawing like this way, see something like that. So this surface is shared by this unit cell and this unit cell also. So this atom will be shared by both unit cell. So the contribution of the 1 unit cell will be, for this atom will be the half, because it is shared by the 2 unit cell. So contribution of the 1 unit cell will be the half. So total number of the lattice point in FCC lattice will be the 1 plus 1, 1 plus 3, that is 3 is equals to 4. So this is non-primitive. We know primitive unit cell having the 1 unit cell, one lattice points, but it is having the 4 lattice points. So this is my non-primitive, and here we have to calculate, we have to find out the shape of the primitive cell of the FCC lattice. So if we have the FCC lattice, see this, I mean this is my FCC one. I'm drawing this one again here. And I'm also making another one. Okay, so the atoms are present at the corner also, at the corner of the cube also here, because this FCC is the known primitive. It has the 4 atoms, so we have to find out the primitive where we can find the only one lattice point. So this will, it is here, 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 and here something. See, if I draw the center of this one to this one, here also similar to this one to this one, and this also, this to this one, and I'm connecting these. Now we have this structure, also this one. So can you tell me this belong to which crystal system? We have option, we have this is the, because see here there is this atom, so this belong to primitive cell of the FCC lattice will be belongs to parallelopiped one, because it is parallelogram, na? This is parallelopiped one. So shape of the primitive cell of the FCC lattice will be the parallelepiped. Okay, let's move to the next question. That is the question number 3. Now, in this question, we have asked the number of the primitive lattice cells in a BCC lattice one. This question has been done in your classroom also. That is taught by the Professor Ashish Gar. So, can you tell me how many the primitive lattice in a BCC lattice? Can anyone tell me about this? Yeah, it will be the 2. How this will be? Let's discuss it. Suppose this is this picture I have took from the classroom lecture. So this is, we have the BCC one here. This is the structure one, BCC one. Okay. So here this atom where we have defined the three parameters A, B, C, where we calculate the lattice vector. So where this is my A2, this is my A3, and this is A1. I have considered this point as a origin. This is my z-axis, this one. This is my y-axis, and inside this one, that is going inside, that is that is my x-axis. This one is my x-axis. So I have chosen this point as a origin. So the my coordinates of the these points will be the, if I'm taking the these lattice vectors. So a1 will be the, this is my a2. So a2 having the parameter, having the length in the my y direction. So the coordinate will be the a2 ay, this one, and a1 is this parameter. So a1 is the this lattice vector. So this atom having the lattice vector, that is having the a1 will be the ax, because this is the cubic one, and so length of the all the side of the cube will be the equal. So my a1 will be the ax cap, a2 will be the ay cap, and here my this center point, the at the body the atom at the body center of the cube having, because this is the at the body of the center. So how we calculate the coordinates of this one? So I have to calculate this vector a3. If I have to calculate this a3 vector, so how we will calculate? First, we will put the projection of this atom to the plane one, because we can calculate the this parameter from the plane one. So if I put the projection here, so this will give me in the xy direction. So this is the xy and this is my z direction. So this point, the what will be the coordinate of this point? This will be the, this is my x direction, this is my y, and this is z. So here it will be the, because it is at the mid of this point, so it will be the a2 x cap plus a2 y cap, and this is point at the body center of the cube. So this will also in the z direction. So this is at the center also. So we have the cube of a length. So at the center it will be the a by 2. So my coordinate for the a3 will be the a by 2 x cap y plus z cap. See, but the thing is here, this body center, you all know about this thing. The BCC lattice having the two lattice point. Total number of lattice point, one is because of the one is because of the atom that are sitting at the corner of the cube, and one is because of the body center, because this body center atom is only shared by the one unit cell. So number of the lattice point will be the 2. Suppose, but how many primitive lattice? Because in the question it is asked how many of the number of the primitive lattice that is in the my BCC structure. So how many we can we have the primitive lattice? If I am assuming this at as origin, so we have the 2. I mean this one, and see, if we say and if I'm saying this one, and if I draw this one also, so this one, if generally we have the 2 lattice point. If I choose this one, this as a lattice point, so it will give me the one lattice lattice atom, and another, if we choose the different set 2, that is having, this is my a1. If I'm as if this is my a1, see, this is one unit cell, this is one unit cell. You have already this question, so I'm just repeating this. And the another one, this is of the another unit cell, because we are choosing for the another unit cell. So this atom this atom of this unit cell, and here this atom of different unit cell, the successive unit cell, BCC successive unit cell, and this of the third that is lying to the right of this unit cell. Okay, so this of because of the third unit cell. So I am considering my A1, that is it is given a by 2, and y cap x. Okay, so it is, because see here it is my in the, this is my z axis, again this is my x direction, and this is my the y direction. So here if I am taking this is my positive x direction going inside, that is my positive x, and so going outward will be the my negative direction. So if I am considering the lattice vector for this atom, so that will be the, because it is lying in the negative x direction, that is an half also, so it's going to be minus of a by 2, and this is in the xyz yz plane also, so this is y plus z. A by 2 is common because it is lying at the midway of the phase. So a by 2 y cap plus z cap minus x cap. Similarly, if I'm taking the a if I'm talking about the A2, there's the lattice parameter. This is my A2. This is lying in the negative direction of your y cap. So that's why here this lattice vector having the minus sign. And see here it is, if I'm saying this way, so this will give me here, it will come out somewhere here. So this is my y direction, so this will be the minus y cap, and this point lying on the this parallel to this point, this face, this atom point is lying to a plane where which is parallel to this one, and for the it will be the somewhere here. If I'm took the projection of this point, so this will be the some projection, and if I find out the coordinate of this point, that will be the a by 2 in the my x direction, a by 2 in the my z direction, and if I the original point, so this is in the my minus y cap, so the coordinate of the a2 lattice vector will be the a by 2 z cap plus x cap minus y cap. Similarly for the a3 also, here this is in my minus of z direction, this is positive one and this is going inside one, so that will give me then the minus ray. And if I draw from these lattice vector, if I draw the, so this will give me this cell, the newly drawn, this will give me this unit cell, and which is having the primitive lattice one. So number of the primitive lattice from the BCC in a BCC lattice will be the 2. Okay, so B will be the right answer. Are you getting my point? Are you able to find out the coordinate of the points? I mean, which one? Primitive, this one? Uh, Second one. Uh, if because this is in the this cell, if you connect this one, and here this is also coming outward, this point also, and this is from the this one. We took these point now here, these one. If you connect them, so this will you will find out this one. This will connect to this way. This will connect to this way. Again, this vector will come out to this origin point, and here also this will, if you connect, this is the translator vector, na? Because this unit cell is coming from the three basically unit cell consecutive. One unit cell, this is the original. If I'm considering the another unit cell that is lying here, and also the unit cell that is coming here, so from there we can connect and find out this primitive BCC lattice one. Can you draw it? I mean, now if I have given you three this lattice parameter, and then you have to connect it. Can you connect it? I mean, is it just a translation vector here? Are you getting my point? I mean, no. Okay, so this is 1 point. Can you draw? I mean, because this is one unit cell. If let's say, how you can assume? I mean, this is in the 3D direction. We have to consider that three cubes simultaneously, three BCC cube one. So okay, if I'm trying to just connect it, I mean, this cell will be the outward one, the because it is typical one to. If, this will be at the center, and here this will be, this cube will be the something here, that is, and here also, So I have drawn new 3 lattice cube. Okay, so the lattice point will be the, this is of the original one, so I'm drawing it the with the black one. Okay, so newly one has the this one. This is the lattice point of this one. This cell that is my from your side, and this point is because of the lattice point that is right to this lattice, this one. Okay, now we have these unit cell basically, and you have to translate it and find out the primitive one where the number of the lattice point 1. So we choose such kind of the lattice where this body center atom will be count as a uh, corner one. If it will count in the corner one, that it will give you the only the number of lattice point will be the 1 if I am count. So I am counting because I am counting all these body center atom as a corner of the cube one. So I'm considering this atom connecting to the this one because this is also the corner one, and this is also the corner one atom. So I'm connecting this to this also. Okay, we have lattice this way. So the downward, this is of the back of one. So this will be this atom will be connected to this one, because this is the at the half of the diagonal one, the half of that this is the diagonal, so half of I'm connecting to this way, and half of this atom, this one, and considering the same the uh, okay, so uh, are you with me this point, with up to this point, I mean this one and this one and this one to this one, is it okay, both these pointer size is too small. Okay, is it visible now, I mean, is it visible now, I mean this point to this point. Let me zoom it this only. I think maybe this will be clear then. See, this is the lattice point, this one. This is the lattice point of the earlier unit cell that we have considered now. Now, okay, okay. So this one, and this is the body center of this unit cell. Okay, this one. So I'm connecting these both, and that will give me the one side of the my primitive cell. Okay. Now I'm also connect. This is too much. I mean, this is another. This is the also the this point. The this point here. I mean, I don't know. This point is also the body center of the next BCC lattice. So I'm connecting these two. So I'm getting one face of this one, and I'm again connecting. Can we get this one face? This one from this one? If I'm connecting both the body center of the lattice point of the both the BCC lattice to their center one, can we get connect this? Can we get this one face of the? And similarly, we have this also. This lattice point is this one. I'm connecting this to this lattice. This is because of the earlier one. This body point is of the new that we have draw. the body center point of the that we draw, and this is the for the new one, this one and this lattice point. I'm connecting these. I'm getting one face from here and another face that is from here, this one, for connecting this one. Now I can connect this to make a unit cell here. Now there is no atom here, this will be go inside this way, and then here all the this say, see this body center of this unit cell is now considered as a consider as a center, the cube center, not the cube center, corner of the this cell, and also this atom already was the corner one. This also was the corner one. This one also the corner one. This one is also corner one. This one is the body center for the this cube one. Now it is considered as a corner one, and here it is also the body center. Now it is the corner one. So I have converted all my body center that are of the different unit cell, I mean the successive unit cell, into the corner one, and so that's why now my all the eight atom are contributing to the my corner atom. So that's why if the contribution of the corner one will be the 1 by 8, so it will give me the one lattice point. That's why this structure will be the primitive primitive one. Are you getting my point? Pani, is it okay now? I mean, should I repeat again? Okay, okay, fine. Does anyone other have doubt in this one? Oh no, this is we have to okay, this one will be the form we have considered from this set too, because we have this origin point. If I'm saying this will be the my origin point. This one. This one. Yeah, I mean, can you say this? I'm just doing this one. Okay. Let's move to the then let's move to the question number 4. The symmetry element not possible in the crystal lattice is the 4-fold, 9-fold, 6-fold, and the 5-fold. See, for a crystal lattice, we need the two parameter. If Bravais lattice, if I'm talking about the Bravais lattice or the crystal lattice, we need the two parameters. One is the symmetry one, and second is the size. If symmetry is okay, then we have to consider whichever having the smaller size, that will be considered in the Bravais lattice. So symmetry, we have the four kind of symmetry. You all know the translation, rotational, inversion. Yeah, it will be the 5-fold one. Any other guesses also? Please check the other also, because these are the multiple one. So you have to check the which other possibility are also there. 9 and 7. 7 is not in the option. So for the symmetry one, we have the four kind of the symmetry, and here we have to. The symmetry is such that we don't have any space or void there. If I am just calculating, so then it will be there will be no space there. So here, so what kind of the four symmetry, n-fold symmetry? N-fold symmetry is basically defined as will be the 360 divided by the theta. Theta will be the rotation angle. So here, okay, fine. Okay, then fine is the 5 will be the correct one. So everybody is saying the 5 one. So 5 1 will be the correct one, because if there will be the some space left there, and also 9 also nine-fold symmetry also does not exist in the crystal lattice. Okay, so because there are the some lattice for this is 5, 7, 9, 11, 13, and 10 also. These are the lattice n-fold symmetry that are does not exist in my crystal lattice. Somewhere they will break down the symmetry or the because cube is not a cube if unless it follow the 4 3 4 symmetry. So this define the that's why the my crystal lattice define upon the my symmetry as well as the n size. So if these one are not allowed, these n-fold symmetry are not possible in the crystal lattice. Okay. Most of you have guessed the right one, but there is the one more option that is also there. That one is the 9-fold symmetry one. Now let's move to the question number 5. So this is the question there you have because there are the some rules for the crystal lattice for the some cubic one. And the for some lattice there will be the some rule which there is the defining symmetry. So here we have to tell about the defining symmetry element for the cubic crystal lattice system R. One is the 3 4-fold rotation axis, one 6-fold rotation axis, 4 3-fold rotation axis, and the one 3-fold axis. So defining symmetry for the different crystal lattice, that is also professor has told you, that is, yeah, it will be the no, it's not be the defining one will it not be the 3-fold rotation axis. It will be the 4 3 4 defining. I mean, if it is not there, if no, cubic generally have the 3-fold, but if that cube does not having the 4 3 fold one, 4 3 4 axis rotation, then it will be not be the cubic structure one. It should be the 4. So defining one will be the 4 3 fold. I mean, 3-fold one. The 120-degree rotation with the 4 4. That having the because we have the 4 body center. From there, we can further we have the 4 1 4 3 4. If any cube having the 3 4-fold one, it may or may not be cube. That's depend it is having the 4 3 4 rotation axis or not one. So the 4 3 fold axis will be the my defining symmetry element for the my cubic system one. So there are the some other defining symmetry for the different crystal lattice. For the cubic one will be the 4 3 fold one because 3-fold we define with the triangle one. For the tetragonal we have the 1 4-fold one. For the orthorhombic we have the 3 2-fold one, and then in hexagonal we have the 1 6-fold one, and in the rhombohedral 1 3-fold one, and monoclinic we have the 1 2-fold one, and the triclinic because triclinic is the most unsymmetric element, so it is not having any kind of the symmetry, so there is no defining symmetry for that one. Okay, so you have to remember these defining symmetry for the different crystal lattice one. So for the cubic one, it will be the 4 3 4 rotation axis one. Okay, is it clear? Okay, let's move to the next question. Question number 6. So how many the possible brevis lattice in 2D? So let's tell me the how many possible brevis lattice in 3D one. In 3D, how many the brevis lattice? How many brevis lattice we have in 3D, 3 dimension? 28. Is it 28 or something else? 14. Yeah. For the 3D one, we have the 14 one. So these are the crystal lattice that having the 14 one. This is the 3D lattice one. Brevis triclinic one, monoclinic one, orthorhombic. In monoclinic we have the simple one and the body centered one. In orthorhombic we have the primitive simple cubic, or this is if you say this is, let's say this is the body center, call it body center for the. And for orthorhombic we have the old type of the crystal structure, and the tetragonal we have the only the cubic one and the body center one. Trigonal we have the only the primitive one. Cubic one having not having the edge center or the face center one. Otherwise, it having the it has having the face center. It is not having the base center or the edge center. Base center or या फिर the edge center that we call. And so hexagonal having the only the cubic one, the simple one, cubic primitive one. Okay, so the for the this 3D hai, we have the 14 lattice systems. And in 2D, so tell me now for the 2D ones, how many are in the 2D? In 2D it's 5. Yeah, in 2D we have the 5 one. First one, where my if this is are the these are my the lattice point. So or and these are my item I am sitting here, where A and my B are not equals, and these are not also the angle between them, because where we have the we are talking about only about the plane one. So here there is only about the plane because 2D. So A is not equals to B and theta is not equals to B. Then what we call this point? This is my oblique one. So we have the 5 Brevis lattice in which where my A and B is not equal and theta is not equals to 90 degree, that is my oblique one. And where the other cases where my A and B are not equals but the angle is my 90 degree, that is my rectangular one. And third one is where my A and C and D, basically C and D are A and B are my equals, but my angle is not now not equal to 90 degree. That is my centered, we call this rectangular centered one. And another where we have the atom that are in the hexagonal first, where A and B, because what we have the only three parameter in the 2D, A, B and this angle theta. So either A and B can be equal or cannot be equals to, and the theta is my 90 degree or theta is not equals to 90 degree. So these are only the 5 possibility that the combination that we come up with this, and also for following the symmetry rule. So we have only the 5 Brevis lattice. So if they A and equals to B are equals, and but the angle is not equals to 90 degree, having the angle that is my theta is equals to 120 degree, that is my hexagonal. There is something like in the same, you all know, in the in the 3D also we have the hexagonal, because these are the same thing 3D one, but we have suppressed to only the 2D two dimension one. So they have the same thing. And where my A and B equals to B and angle between them is 90 degree, we all know this is my sphere one. So we have only the 5 derivatives in the my 2D 2D. Okay, so these are the 5 one. Okay, so this question is all about the number of the possible probabilities in my 2A, because if I'm taking the combination, so that will be the, if it's see the this A and equals A and B can be equal, so two combination will be either A equals to B, theta equals to 90 degree. This is giving me the sphere, and the second one can be the A equals to B, but theta is not equals to 90 degree, that is my the centered one. And then the third possibility come up now, a or A and B not equals to B, but theta can be 90 degree, that can come under my rectangular one. And then if my A and B is not equals to B but theta is also not 90 degree, that is my oblique one. And if A and B are equals but theta is not equals to 90 degree but it is having the 120 degree, so this is my the hexagonal. That's why we are having the only the 5 Brevis lattice one. So okay, let's move to the next question. So tell me the which of the following crystal system consists of the space lattice with two distinct lattice parameter? You all know about these crystal lattice. Let me tell you again, and then you have to tell me which of the following crystal system having the space lattice with two distinct lattice parameter. In tetragonal, you all know A1 is equals to A2 but not equals to A3. In orthorhombic, we have A1 equals to not equals to A2 but not equals to A3. In hexagonal, we have A1 equals to A2 but not equals to A3. In triclinic, we have A1 is not equals to A2, not equals to A3. So which of the following crystal system consists of the space lattice with the two distinct lattice parameter? So all the parameters are given here and you have to select and tell me which of the following crystal space lattice having the two distinct lattice parameter. You have to find out two. We have the three lattice parameter. The trans here it is they have talked about the only the translation because we have the lattice side, so only will be the translation. So which of them will have the two distinct lattice parameter? A, B, C and D. Which will be the one? Will it be the tetragonal, orthorhombic, hexagonal, or the triclinic one? A and C, yes. Because here these two sides are equal but three different. So we have the two distinct lattice parameter in the tetragonal one and in the hexagonal. So A and C will be the right answer for this one. Okay, is it clear to everyone? I mean, up to this point, do you have any question? If you have any kind of doubt, so let me know, please. I mean, this is more of this is not the one side way of solving problem. This is the discussion type tutorial. So you have to tell me so we can discuss so that we can discuss. I mean, okay, okay. Then if you don't have, then let's move to the next question. That is question number 8. So there is no add centered cubic lattice because you all know about the and centered cubic one. That is my, if this is my lattice. Oh, is it the S end centered one? No, it is not, because in the end center we have only two atom at the two face, that is opposite to each other. So this will be the my end centered one. Okay, so this is my end centered one. So you have to tell me why this is not existing in my cubic one. I saw you, I show you there because it is in the cubic one. If I'm check here, see in the cubic one this is not existing. So why this is not existing? It is already done in your classroom also, I guess. So you have to tell me why it is not existing in the cubic one. If I draw the another lattice here, A, uh, it can be represented by a simple tetragonal lattice. Okay, okay, let it assume it A. What about the, can it be represented by the simple orthorhombic lattice? Or it violate the symmetry of the cubic lattice one, and or it is not a lattice at all. Does any other option will be the will be for this one? No end centered cubic one. See, if I'm drawing the this one from this cell one, edge center, another lattice from this I'm trying to say, this is S, and if I'm connected these one, so I am getting this kind of lattice. In the tetragonal, we have found out this is A, we know A equals to A1 equals to A2, but not equals to A3. Okay, so here these side are equals, but not equals to this one, because here it is having the simple tetragonal or the simple orthorhombic. In orthorhombic, this for the tetragonal we have this condition, and for the orthorhombic one we have A1 is not equals to A2, that is not equals to also A3, but we are having this side and this side are equals, but it is not equals to this one. So I can represent this my end centered one to the simple tetragonal lattice. Okay, so my A point is right. So B will be not be, because two sides are equals, third one is the different one. So what about the third one? It violate the Smith. So why it is, I mean, why there is need of the simple trigonal lattice if we having the edge center thing one? So why we are having the this trigonal one? We can do all the calculation with our edge center cubic one. Then why we need the this tetragonal one? So is there any other option that is going with this edge center cubic space lattice? If I talk about this cubic lattice having, we have already told you, because the defining symmetry for the cubic one is the, what was that? Now you have to tell me. 4 3 4 symmetry. Okay, and this is diagonal one, because if I'm these are the because we have the four body diagonal one, and if I'm doing it, so the rotation about the body diagonal will be not be symmetric for this point, because these are at the opposite center. These are not lying here, so this will, it will not be symmetric about the diagonal one, so it will not follow this symmetry. So that's why it violates the symmetry of the cube lattice, and it does not come under the cubic one. So this so that's why this edge center cubic lattice does not exist. First, it can be represented by the simple tetragonal one, and another, it violates the symmetry of the cubic lattice one. So the A and C will be the right answer for this one. Okay, is it clear to you? Okay, so we, in the next question we have, you have to calculate with the angle between the two different plane. We have the two different, each plane is defined by the HKL number. So that is 1 1, when another plane is 1 1 2 minus plane in the cubic lattice, and you have to find me the you have to tell me the angle between these two planes. We know if we have the two planes, that is H1 K1 L1, and another plane having the indices H2 K2 and L2, these two, and if I to have to find out the angle between them, with cos theta will be the H1 H2 plus K1 K2 plus L1 L2 divided by H1 square plus K1 square plus L1 square, then H2 square plus K2 square plus L2 square, and then whole under root. So this giving me the angle between the two different plane. So tell me the angle between these two planes, how much it will be. You have to just put the, here your H1 K1 and 1 will be, this will be the 1 1 1, this plane, and this is 1 1 minus 2 1. So tell me the angle between them. So this will be the 1 into 1 1 plus K1 K2 is 1, 1 into minus 2, this is minus 2 under root 1 plus 1 square plus 1 square, that is 3 square under root of 1 square plus 1 square plus 2 square. This is giving the, this is cancel out, this is giving me the 0. This imply cos theta equals to 0, theta is equals to 0, or is it something else? So your theta will be the 90 degree. So angle between these two planes will in the cubic lattice will be then both are perpendicular to each other. Okay. So if you have to find out the angle between the two planes, there this is the formula for the cubic one. You have to calculate, just put the value here, h1, k1 and l1 and h2, k2 and l2 and find out the angle. Take the inverse of the cos. Don't forget about take the cos inverse of the value there if whatever you are getting. Other because the option here it is also given the 0 degree, but the cos theta you have to calculate, not only the cos theta one. Okay. So this is the easy one. So next move to the question number 10. So multiplicity of the one plane in a cubic plane in a cubic crystal system. If we have a cubic crystal system considering the negative indices as a separate, you have to tell me, see, each plane is represented by this one, HKL, and if I'm talking about the family of planes, so that will be represented by HKL. So here this family of plane, so how many multiplicity of this family of plane? You have to calculate how many planes are existing to this family. Similarly for the direction, each direction it is represented by this way UVW with the full bracket, and if I'm talking about the family of direction, that is represented by UVW with this bracket. Okay. So now you have to tell me the multiplicity of this 100 family of plane in the cubic crystal system. What will be the multiplicity of this plane? So this will include the 100, another it will be having 010, another it is having 001, and because it is also we have to calculate the negative indices as a separate, so it is also having this a negative 100 minus 10 and 00 minus 1. So is there any other possibility? So only the six planes are possible in this family. So multiplicity of this family will be the sixth one. Okay. So move to the next question will be the choice of the unit cell. This is so easy. You have to tell me. So the choice of the any unit cell will be unique, not unique, fixed one, and none of the above. So what will be the choice? Can we, is there any condition that, I mean, is the choice if I'm defining, somebody is defining if this is the my lattice point, this, somebody can choose this as a, and somebody also can choose a, this as a unit cell. So is the choice of the unit cell is unique or not unique or fixed or none of the above? Yeah, it will be the not unique one, because somebody can choose this one as a unit cell, somebody can choose this as a, and somebody can choose as another one also, this one or this one. So this is up to the user how they choose their unit cell. So it is not unique one. Move to the next question now. Again, this is similar to the earlier one we have already discussed. So find out the multiplicity of this plane in the, there we have calculated in the cubic one. Remember this thing, there we have calculated in the cubic one, and now you have to tell me for the tetragonal one. In the tetragonals, what is the multiplicity of this plane? In the cubic we have the all side are equal. In the tetragonal, we have two are equals, but not equals to the third one. So the multiplicity of this plane will be in the tetragonal crystal structure will be. Now this is similar to the earlier one that you have to now you have to tell me what will be the multiplicity of this plane, this family of plane. Will this 100 will equals to 001, or will it be equals to 010? See, because here the all the sides are not equals, only the two sides A1 and A2 are equals to, and they are not equals to A3. So this plane is equals to this plane only, but not equals to this plane. So if I'm talking about this family of plane, so this family of plane will include only this plane and this plane, because A3 is different, so this is not including this one, and it also include the negative of this point, these, because we have to consider the negative one. So it can be the -1, 0, 0, and also 0, -1, and 0. So how many will it be? Is there any another possibility other than these? No, because we have already considered the negative one also and the positive one. So there are only the four plane is included in this family. So the multiplicity of this family of plane will having the four, only four one. And if somebody told you how to find out the multiplicity of this family 110, how many will be for this one? How many plane does this family are having? So it will include, similar, it will be the, I'm talking about the tetragonal, not the cubic one. So you have to consider this thing. As it talks about the cubic one, which of the crystal structure it is asked in the cubic one, tetragonal, or the other one. So you have to consider the lattice parameter in the what are the lattice parameter in that crystal structure, and then after you have to think about which of the plane are in the possible in that family. So for this, if I'm talking about the tetragonal, so this will include 110, -1, -10, any other? Because it is 0, so then it will also include other one also. No? -1, 10, 0, -1, 0, and this will be the, so it will include only the 4 one. So in the next question, find out the spacing between this plane, 1 plane in the FCC crystal structure. The spacing between the 1 plane in a FCC crystal structure is 2 angstrom. The lattice parameter and the atomic distance are. So how do you calculate the lattice parameter and the atomic diameter for the FCC crystal structure? You know, in FCC, if I'm doing the only the one face of the cube, so this is the my center atom, and all the atom that are my present at the corner. Okay, so this is my, now this is the my one of the phase one. If R is the radius of my atom, A is the side of the cube or the lattice parameter 1. Can you tell me the relation between R and A, because this is my face diagonal. So what will be the this one? Because this is A, this is R, this is my 2R, and this is my R. So what will be the relation between R and the radius of the atom with the lattice parameter? See, first we know the distance, interspacing between the between the plane will be the d will be the a under root of h square plus k square plus l square. Okay. Now they have given d is equals to 2 angstrom. So you have to find out the lattice parameter, that you have to calculate the value of a, and HKLR equals to 111. So D will be that is my 2 equals to A under root of 1 square plus 1 square plus 1 square. That give me A by root 3. So A will be the 2 root 3 angstrom. So lattice parameter will be the 2 root 3 angstrom. Now you have to calculate the atomic diameter as well also. So atomic diameter, if I see from this face of the FCC1, so this will be this is also my A, this is the cubic one. For the cubic one, this is also my A. So this face diagonal will be the A into A. This will be the 2 root 2A, and this root 2A, because this is the my FCC one. So this include the R plus 2R plus R, that is equals to my 4R. So this is my relation between my lattice parameter as well as with the radius of the atom one. So root 2A is equals to my 4R, and we have to calculate the R radius will be the root 2A into by 4, and that we have already calculated the A. Just put the value here and you will find out this will be equals to how much? 2, and this you can write it, this will be the again you can do this one, 2 will be the root 2, 2 by root 3. Okay, okay, so this will be the this one. So root 6 by 2, this is the atomic radius. Now here it is asked the atomic diameter. So what will be the atomic diameter? Atomic diameter will be the 2R. So 2R will be the root 6. So atomic diameter will be the root 6 angstrom, and the atomic parameter is the 2 root 3 angstrom. So A will be the right answer. Okay. So is it clear for everyone? Is it clear for everyone? If somebody asks you the body center one, here it is asked about the FCC structure, crystal structure. And if somebody has asked about the BCC one, so what will be the relation between the your lattice parameter and the atomic radius? What will be that one? Because in there we have, along with the corner of the cube, we have the atom at the center one. So we have to consider the center, body center also, atom, the body center one. And we know the what will be the, because here it is also the atom there one also, here all the atom are packed. So what will be the body diagonal of a cube? What's its value? So body diagonal will be the root 3a for cube 1. Again, your in the body diagonal, if I'm taking that face, so this, if this is your body center one, other atom will lie here. So again, so this root 3a will also equals to, this is because this will be the 2r, this will be the r, again this will be the, so root 3 will be equals to 4r, and your 2r, or 2r, yeah, the diameter, atomic diameter will be the root 3 a by 2. This for the BCC lattice. And the for FCC, we already discussed root 2a equals to 4r. This is for your FCC lattice. And the for simple cubic, you have a is equals, you don't have any other atom, so you have only at the corner of the cube, so a will be the 2r. So remember these relation because it will be helpful for calculating the numericals if you have to find out the relation between your lattice parameter and the radius of the atom one. Okay, okay, so is it clear for everyone? Is it clear for the all the crystal structure, FCC, BCC, and the simple one? It's not all about the FCC crystal. If somebody has given you for the BCC one and the CMYK one, I'm assuming that you will calculate. If you remember these relations, and then you can calculate for the simple BCC and FCC as well. Okay. Move to the next question. So, number of lattice point in a rhombohedral unit cell. It's clear, ma'am. Okay. Number of the, so tell me the number of the lattice point in a rhombohedral unit cell. So I want to tell you rhombohedral is your same trigonal lattice. Someone called the rhombohedral, somebody called the trigonal. It is the same equivalent thing. So you have to tell me the number of lattice point in the rhombohedral unit cell. If I go to the crystal lattice system, so rhombohedral having the this system, or the, if I'm talking about the lattice condition, so the this is having this one rhombohedral. A1 equals to A2 and equals to A3, but alpha, or yeah, alpha equals to beta, beta is equals to gamma, but that is less than 90 degree, or you can say that is less than 120 degree, or yeah, that is not equals to the 90 degree. So how many the lattice point will be the rhombohedral one? Because here angle, this one is different one. The angle between one, this one, if I'm talking about this one angle, so this angle is different one, but and A1, A2, and A1, A2, and A3 above all are equal, so only the angles are different there only. So how many will be the lattice point? Because all the atom are only at the center of the rhombohedral structure, so they are contributing only to the one, because one eight atom, and one of the atom is contributing only the 1 by 8, so total number of the lattice point will be the 1. So number of lattice point will be the 1, so D will be the right answer. Yes. So move to the next question, that is question number 15. The tetrahedron has 8 faces, 6 faces, 4 cases, 4 corners, or eight edges. Which of the following is having the tetrahedron? Tetrahedron having the 8 faces, 6 faces, 4 corners, and the 8 edges. How many? Which one are the correct? Which you know about the tetrahedron? What is the tetrahedron? Somebody told me the eight faces and the eight edges. No, that is not the tetragonal. Not the tetragonal. Tetrahedron. This is your tetrahedron. Now tell me how much faces it is having, how many edges are there, how many corners are there, and this is your tetrahedron. Okay, this is this is not equal to your tetragonal. Tetragonal cubic system are different one. So it is having the four corner and the six edges. Yes, it is having the, somebody told me it is having the four edges, four corners and the six edges. How it will, how it is having the, okay, four corners. I think you can see this one. This is the one corner, second one, third one, and the fourth one. What about the faces? How many faces it is having, and how many edges it is having? How many faces? Don't go with the option. Just tell me how many faces it is having. Just count it from here. How many faces do you feel it having? Cube having the, the cube having the, how many faces the cube having? If you can tell me. Cube one for the cube. How many corners is and the face for the cube, and how many corner is and the face for the tetrahedron? Somebody has given the right answer, so others can tell me for about the cube one. For the cube one, for the cube one, how many faces it is having? In the cube, how many faces are there? Aces you can count. How many are these? Four here, four downward, and then four here. 12 aces. In cube one, you have the 12 aces, eight corners, one, two, this one, 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 and this one. Eight corners. Eight is 12 edges. This you can calculate from here. These are the 12 one. And the how many faces? For the cube, yeah, it will be the six faces because the four from the because four will be the one will be the that is behind one. This one will be the that is from your side, and these two are one is in the left, another one in your right one, two are upward, two one is upward and one is downward. So total number of the faces one will be the six faces one. Okay. Similarly, in the tetrahedron, how many will be the corners? So four will be the corners ones. One, two, three, four. Four one is a, how many edges are there? One, two, three, four, five, six. So the four corners, six edges, and how many faces are there? Faces. Just tell me about the faces. How many faces it is having? For the tetrahedron, what? How many faces it is having? Faces. You have already told me about the edges and the corners one. Now for the how many faces it is having? Is it the eight? Because answer is I mean the option is having the 8 faces. So does that tetrahedron having the 8 faces? Yeah, it will be the 4 faces one, because one will be the this one, another one this one, and one will that is in the backward one, that face only, and one that is in the beneath of this one. So it is having the 4 faces, 4 corners, and the 6 edges one. Okay. Uh, let's move to the question number 16. That is the what is the coordination number of FCC crystal structure? So what will be the coordination number of the FCC crystal? This is FCC, you all know, I have done already. So you have to tell me what will be the coordination number of coordination number, as you all know, I guess coordination number of the nearest number. The coordination number is the number of the nearest neighbor atom. So how many for the FCC1? So coordination number with the number of the nearest neighbor ones. For the FCC, you have to tell me the how many will be. So okay, if I consider the simple cubic first, if I'm just a simple cubic, this one, what will be the coordination number for the simple cubic one? If I'm considering this atom, so how many atom will be the nearest to this atom? This one. If I'm considering this as the origin, so how many atom will be the nearest to this atom, the origin or A? How many it will be? Now you don't have to consider the only the one single unit cell. You have to consider complete crystal, and there you have to find out the how many nearest neighbor one. So for this one, this is one, this is at the same distance, because all in a simple cubic you have the atom at the corner only. So this one will be the one, this one will be the one, this one will be the one, and there will be the there also, and there is also the at the back one, and there also here also it is. So how many it is having? So what will the coordination number for the simple cubic one? If I'm considering for the simple cubic, what will be the coordination number? See, if I'm considering this as an atom, so how many will be the nearest neighbor to this atom? This will, because this is also at the A distance, this atom also at that distance, and this atom, this is of the different lattice, that is behind this lattice one, so that is also at the A distance, and this lattice here also again there is another lattice, this is also at the A distance, that is the left of this unit cell, and above one also, and the below one also. The coordination number for the FCC simple cubic one will be the sixth one. Now you have to tell me the coordination number of FCC1. So how much will be the for the FCC and the BCC? Tell me for the one. I mean for the BCC, either tell me for the BCC, or tell me for the FCC one. If I'm considering This atom okay, let's take this example, the FCC one, where the atom are at the corner of the unit cell and also at the each of the center of the phase one also, and we have to find out the nearest one. So there, because each phase also having the this atom, so here, so this phase, this plane is having this center atom, this is having this one, and this one also the back one, this plane also having this one, and the front one also having this one. So these all four atoms are in the same plane, are at the same level also. Is it so or not? Yeah, it is at the same plane. Okay, so what would it be, the this one is the nearest one or the this one is the nearest one? You have to tell me. Which atom is the nearest one? This one or the two one? If I'm considering this atom, so which one is the nearest? Either one or two. This is the cubic one. This is having the side A. And so which one will be the nearest? One or two? This atom or this one? See, atom A is at the distance A, and the atom 2 is at the distance because it is the phase center, and this diagonal, phase diagonal is of root 2 because A and A here, and it has the midway of this phase diagonal. So distance will be the A by root 2. So which is near to this atom, this center atom, A or A by root 2? Yeah, 2 will be the nearest one. Now it is clear the corner atom are not the nearest one. Okay, now we have to find out the how many are the nearest one. If I'm considering this atom, so you have to tell me, so how many will be the nearest one to this atom? Because these atom, the corner will not be the first nearest atom, these will be the second nearest, but the coordination number is the nearest atom. So these atom will be the nearest one. Whatever at the phase diagonal, at the nearest one, if I'm considering this one, so how many will be there? Now this is the question. Because this atom is this one, or consider this atom or either this atom, because all are at the same distance. So how many will be the? Just tell me how many will be the nearest one. No? Okay. Let me draw for an easy one for you guys. Okay, let's see. I'm considering the two lattice point here. And I'm representing with this one as a green color. So now this is clear, the face center one will be the nearest one, so I'm considering on the face center. For this plane, this will be the somewhere here. For this plane, center one, this will be the somewhere here. And for this plane, this will be the somewhere here. Again, for the this center one, this one, and again for the another one. So if I have already told you these four atoms, that is in the, if I'm considering this atom, because these are the four. This one, and okay, don't consider this one, otherwise you will get confused. Okay, so I'm considering this atom for your convenience. This is the one. So these are at the this one because this is the phase diagonal one. This is at if I'm considering this one here, there we are considering this atom, and then we are taking about talking about this one phase diagonal center one. But I'm considering the phase diagonal as a center one so that I can find out now for making the for the convenience we have chosen this atom, and now we are finding how many are the nearest to this one. Same thing you can consider here. For here you can visualize easily, so we are discussing here this one. If I'm considering this one, so these are as the because this has the phase diagonal root 2 by root 2, nearest will be the root 2 a by root 2. So 4 are here, and the how many are others? I mean now you have to consider the upward one also and the lower one also. So how many will be there also? 4 one that are lying to this plane, and 4 other because these are the 4 atoms that are also in the one plane. If I'm considering the this one is at the center, see this one, here it will be this one and the this one. 4 atoms that are these 4, this atom, this atom, this atom, this atom, this atom. Okay, all are considered 1, 2, 3 downward, and this one. So these four are at the same plane. This one, this one, these four, and now this atom again here also the same plane. Now we have considered this plane here. The four are this on this plane, and now this is the another plane where these four plane and these are also at the same distance, a by root 2 distance. The distance, are you getting my point? I mean this at the center, and this distance is a by root 2 a by 2, because this is the distance between them is this is root 2 root 2a, and it is at the midway of, then it is a by root 2. So this atom, these four atoms that are lying, because in the cubic one we have the four face that are making the cube one. Not the, don't count the upper one and the below one, the below plane, the four other plane also, because the four other plane also having the atom at their center, so they are making the one plane there. Let me consider if anything I have. Okay, this if I'm considering this as a, if this is a cube one, I consider this as a cube one. I mean this face, this face, this face, and this face all are having the center atom, and all these atoms are at in the same plane. And if I'm considering atom that are presented here, so this atom is equivalent to distance to this atom, this atom, this atom, and this atom. So it is equivalent to the corner of this plane as well. I mean corner this, consider this as a cube one. So this atom is this the atom that is present at the center is equidistant to all the corner atom of this plane, and also this is at the center one. So this is equivalent to the center of these plane one also. So the at four atom that is below this plane, and the four atom that are above this one. So four here above one, four in this plane, and four in the below plane. So total number of the 12 atom that are in the that are nearest to this atom. So for the FCC one, the coordination number will be the 12 one. Are the nearest atom 6? No, no. Nearest atom, how it will be the sixth one? No, because here this plane also having the 4 atom also as well, na? And this one also. So 12 atom will be the nearest one. And the 12 atom are the nearest one, so the coordination number is the 12 one. For BCC one will it will be for the BCC one it will be the 8 one. For FCC it will be the 12 one. For BCC you have to consider the BCC took as a BCC atom for the see I don't are you getting my point? I mean for the BCC this is the simple one because the atom is at the center and the all the corner atom are at the same distance, so the total number of the nearest neighbor will be the 8 one. For the FCC one this is face one is at the center, so this plane also having the 4 atom that are equal, another plane also having that the same distance, and another plane that is also equals to 4 here, 4 here and 4 here, so total number of the 12. So that's why the FCC is having the 12 coordination number, simple cubic having the 6, FCC is having the 12 and BCC having the 8 coordination number. Okay. Okay, so do you have any doubt till this, I mean, till this point? Is it clear for everyone? I mean, the nearest number for the FCC and the BCC and the simple one. Is it clear for everyone? Do you have any doubt in other question as well? I mean, till this point, up to question number 16. Does anyone has any doubt? Some people has joined the late in the classroom. It's clear, man. Okay. So some people have joined in the late. So I'm just going through the only the question, all the question. If somebody has in doubts in any of the question, stop me there. We will discuss that one. Otherwise, we will wrap up this one. So in the first question, we have a unit cell, and there is the lattice parameter here. Different lattice parameter is here given, and there we have to find out the what is the space lattice, which of the crystal lattice it is having, all the lattice parameter, lattice one are different and the angle are also different, so this belongs to the triclinic one. Okay, in the next question they have asked about the primitive cell of the FCC one. If I'm because FCC having the 4 atom, so we have to find the shape of the primitive one. There if we draw any figure where we can find out the only the one atom from the primitive one, so what will be the primitive cell? What is the shape of this one? The shape of the primitive FCC one will be the parallelepiped one. Okay. In the third question, they have asked about the number of the primitive lattice in the BCC lattice. So yeah, yeah. Tell me, on Murugan. Sorry, I can't pronounce your name clearly, I guess. So what's your doubt? You can unmute yourself and can ask question. You can unmute. Either you can write your question in the chat box, or you can unmute and can tell me what should I. No, it's not cubic. It's not cubic. It will be the parallelepiped one. It's not cubic one. Yeah, it's not cubic. It will be the parallelepiped one because it's because the angle between them is not the 90-degree. So that's why they are making the parallelepiped one. The side are also these side are also not equals. These and these are not equals, and angle between them also not equal. So this is the parallelepiped one, not the cubic one. Okay, is it clear? One Murugan, is it clear? Muthuswamy. Is it clear? S. What one? Which one? S. I didn't get your point. No, it will not be the cubic one, it will the parallelepiped one. Okay, it's clear now. Okay. So in the third question, they have asked about the number of the primitive lattice in the BCC. BCC having the two lattice atom, and we have to find out the number of the lattice, primitive lattice in the BCC one. So it will be having the 2, 1. So in the fourth question, what is the symmetry element that is not possible for the crystal lattice? For either it will be the threefold, ninefold, or what? Which one will be the? So we know the symmetry elements that is that should be don't have any space there. So this one B and D, that is 5, 7, 9, 11, and 13 and 10 fold crystal symmetry does not exist. So the B and C will be the right one. So the fifth question they have asked about the defining symmetry element for the cubic one. Cubic one, we have discussed all the defining symmetry for the all the crystal structure. Just go through them, and these are the for the cubic one will be the four threefold symmetry one. In sixth one, they have asked about the number of the possible previous lattice in the 3D, that is 5, and in the 2D it is 5, and in the 3D one it is having the 14 one. In question number 7, they have asked about the this parameter of the different crystal lattice, I mean, which are having the distinct lattice parameter. From them, among them, I mean, you have to find out which are not having. It is clear from we have given the this parameter. Just remember the crystal structure, which are the parameter for the what crystal structure, so that you can find out for them what for them, I mean, which of the condition is fulfilled by which crystal structure. Question number 6. Repeat the question number 6. Okay, so how many possible Brevis lattice in the two-dimension one? So the in the two dimension in the 3D, it is clear we have the 14 one. I'm just going through the all the 14 and then we will discuss. Okay, okay, let's first do the 2D one. In the 2D, we have the only the three parameter, that is A1, because we are talking about the two dimension. Two dimension there, what can be the possibility having? But either will be the A1, A direction in the X direction, and the parameter in the Y direction, that we have defined the A1 and A2, and the third one is the angle between them. So what can be possibility for them is one is having they can be equal, a1 a2 equal, but theta is, because we are defining theta may be 90 or may not be 90, so theta is not 90, and another condition can be having this theta is equals to 90. Two possibility are this one, and we have defined this one. This is my sphere one, and a1 n equal to and a is not equals to 90. This is my the oblique one that we have discussed here. Another possibility, now we have considered the both the lattice parameter are equals, but now it is possible that this both parameter are not equals to. Now a1 and a2 are not equals to, but your okay, A1 and A2 are not equals to, and theta is equals to 90 degree. Another can be possible, A1 and A2 are not equals to, but theta is also 90, not also 90 degree. So 1, 2, and 3 and 4. These are the four, and fifth one, because the theta we have put only the condition on the theta is equals to 90 degree. There is a possibility there also where A1 equals to A2 and theta can be the 120 degree. So these are the five possibility, the five Davis lattice that is existing in my two dimension one. Is it clear, Ankit, now? And this angle is my the center rectangular one. This is sphere one, and these are my rectangular one. This is my if not equals to it, this is the my oblique one, and this is my the hexagonal one. Okay. In the 3D, we have discussed the 14 one, that the 14 lattice one, because each lattice having the can be of the four type, that is the simple cubic, face center, body centered, and the A center. So it from the if I just look at this one, so it should be have the 28 in the 3D. 28 Brevis lattice, but we are not having the 28, we are having only the 14 one, because of the symmetry and the similar size, because some of the crystal structure are either they convert to the another one, and some of them they are not fulfilling their defining symmetry condition, so that's why we are only having the 14 Brevis lattice one. So in the question number 4, this is all about the crystal structure. And in question number 8, so why this is the end-centered cubic lattice one is not existing? Because it can be represented by the my simple tetragonal lattice, or it also violate the symmetry of the cubic lattice one also. So in 9, you have to tell me the angle between the different plane. You know about the different plane, how to calculate the angle between the different plane. If we have given the two planes, so we can calculate with the angle between them. That is the cos theta is equals to h1 I mean with this formula. Remember this one. You can find out the angle between the two plane if the two planes are given. For question number 10, you have to calculate the multiplicity of this plane in the cubic one, and there is another question over there also. There you have to find out the multiplicity of the this plane also, but in the tetragonal. So always remember the condition for the each crystal structure so that you can find out. So multiplicity for the cubic one, it will be the 6 one, and if I take the same question for the tetragonal, there it will be the 4 one. Okay, so in question number 11, the choice of the unit set is not unique because somebody can choose this lattice, somebody can choose this lattice, and somebody can choose this lattice. So this is not unique. This can be anything. So the choice is not unique for the user one. In 12th question that we have already discussed, in question number 13, what is the spacelet is the spacing between the plane is given for the FCC lattice crystal one, and then you have to find out the lattice parameter, what will be the lattice parameter and the atomic diameter. If you remember the atomic diameter and the lattice parameter relation, there you can calculate the either of them, and from the d spacing distance with this formula you can calculate the a or d whatever the condition is given. Others I can find out from this using the this formula one. Okay, in question number 14, you have to find out the number of the lattice points in the tetragonal rhombohedral units, and because go through the all the crystal structure. From there you can find out which of the following is possible for which crystal structure, because and how many are the lattice point for that crystal one. For the rhombohedral, because all the atoms are at the corner of the rhombohedral structure, so so only one lattice point that is existing for this one. In 16, the tetrahedron is how many faces, edges, and the corners one. So tetrahedron has the four corners, six edges, and the four faces also, six faces also. Six, yeah, six or four, one, 4 faces one. Sorry, four corners, six edges, and the four faces one. And then the next question, the coordination of the FCC, we have discussed with the coordination number of the simple cubic, that is my E6, and for the FCC one it is 12, and the BCC one is the 8. So this is all about the assignment 2. If you and these are the lattice 3D lattice system, all of them, and what are the condition, what are the parameter for the each Brevis lattice one. So this one, and also this is also the another diagram of the this cubic structure one. So it about the crystal structure. If you have any doubt, please let me know. We will discuss this one, that one. So any one of you have any doubt in any of the question or in the lecture theory also? If you have any kind of doubt, please let me know. Please unmute yourself and let me know, please, if you have any doubt. Please define the primitive lattice vector. Okay, primitive lattice vector is basically there we have. I mean, it's see, we have only the because we have existing. If somebody asks you the primitive one, so there you have only considered the only thing that their atom. I mean we have to consider such units are there is only the one atom. One lattice atom should be there only. There is no other condition you have to think about which with the which lattice vector there that you can use and find out the lattice. They are in the FCC or BCC that we have discussed. In the we have considered such that because all the my center atom become my this corner one there only. So that's why they become my corner one, and they are contributing to the only one atom. So lattice vector is the same thing. I mean the vector is not the different thing. Vector is the basically your, if you have two atom there and if you are choosing the origin this one, so this will be the your lattice vector one, whatever you are. So you have to choose the atom such that so that you it become the primitive one. If I'm considering the body center, so I'm considering this body center to use to become this as a at the corner atom so that it can become the my primitive one. For the FCC there also we have used such that such at the such, I mean such origin, and we find out this can become a primitive one. So this all about the primitive lattice vector. I mean, you have to consider the lattice vector that is giving you the primitive units, and lattice vector is the vector between the, I mean, the direction of the between the 2 points. If we have to go through any direction, so how we will define that, we will define with the lattice vector one. Pani, is it clear? I mean, okay, okay, okay. Center point of the phase. Okay, considering okay. Vector is basically direction. Normally, whatever the vector we are having, because vector having the magnitude and the direction one. The vector is just only the direction that is giving you direction only. There we are choosing a lattice vector such that we are getting the primitive lattice one. Are you getting my point? I mean, vector is the same thing that we are considering the math one. I mean, vector normally that is having the magnitude because there is nothing with the magnitude. In the primitive, we are considering only the atom that is giving the only the number of unit lattice point is only one. So it is not about the how much is the magnitude one. So we are just defining the whatever the direction in which direction we should consider our lattice so that we can get the primitive one. Is it clear? I mean, I don't know. I mean, is it clear to you now? I mean, or you want to something else? You want to ask something else? I mean, Ani, is it clear? I mean, okay, okay, fine, no problem. I mean, you can mail me or you can ask some. I mean, we will discuss again this one. And what about the others? I mean, do you guys have any other doubts? I mean, could you please request the professor to increase the pointers, how he might be pointing at something which I could not locate and hence difficult to follow. Okay, okay, I will ask, I mean, I will mail him and kind of ask the professor to increase the pointer. Yeah, sometimes it's difficult if we are using any kind of the photo, so it is difficult because the pointer size is too slow. You can ask there in the classes. Don't you follow the classes in the classroom at the timing, or are you watching the video in the later time? I mean, okay, okay, video, video later time. Okay, okay, then I will ask the professor, I mean, to increase the pointer size, and I will mail him, and I will, and you can also put on the uh, form. There is a form, doubt form, I guess, on the portal also. There you can also doubt yourself. If you have any doubt, you can ask there also. The professor as well as us also kind of keeping eye on that one also. There you can also, that will help, also can help you. And I also will mail the professor one. because the thing is about it's all about the class when he is using. If he will receive the mail, I mean, before the class, then he will use the pointer of, I mean, of the bigger size. Otherwise it will not be helpful for you. So it's better to take the physics form and put this query there, and because before the classroom I will go through that one, so it will be helpful. Anyway, I will mail him, I mean, for definitely I will mail him and he will do it that one. So any other, okay, Pon Murugan, can you pronounce your name? I mean, Muthu Shami, I mean, I don't know how to pronounce it, so it will be difficult for me to pronounce. So just let me know so that I can pronounce clearly and correctly also. Pon Murugan, okay, Pon Murugan, okay, Pon Murugan, okay. Okay, so no doubt for from the Pon Murugan and the Pani. What about the Pani? Doubt. Okay, this is the doubt that you have to go through. Okay, 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 all clear. For that or that also, because they are not messaging, I'm hoping it's clear for everyone. So you can leave for now. I mean, if you don't have any doubt, I mean, you can leave now. Tino Tinda, I mean, you can also leave the group if you don't have any doubt. Okay, thank you. Tino Tinda, are you there? I mean, Tino Tinda, can you hear me? Do you have any doubt? Yeah, Tino Tinda, do you have any doubt? I mean, you, sorry? No judgment. Okay, okay. Thank you. Thank you.